Hi friends! So today we are going to talk about entropy, free energy, and thermodynamic favorability. So essentially everything in the universe is really designed to be lazy. It wants to be in its lowest possible energy state. It's comfortable for it to be there. In a low energy state, we can say things are thermodynamically favorable, which literally just means it's a good place to be. That's where it wants to be. It's happy being there. It puts itself in a low energy state. So you can think about it like if you take an ice cube and you put it out on the take it out of the freezer, put it into the room, it's gonna melt no matter what. You can't keep that ice cube frozen if you take it out into room temperature. If you leave your bike outside, eventually the chain's going to rust. But if you have a pencil and the graphite that's in your pencil is just made from carbon, that carbon is never going to turn from graphite into diamond. So why? Why is that true? So how can chemists determine if a reaction will occur? That's what we're going to take a look at in this lesson. So our definition of thermodynamic favorability really describes a process's ability to occur without external intervention. So really what this means is that it's going to happen no matter what, but it doesn't necessarily mean it happens quickly. Think about your bike scenario, right? You take your bike out, you leave it outside for a while, eventually those chains are going to rust, but it doesn't happen overnight. It doesn't happen super quickly. It does happen over a period of time. So it just means it's going to happen without assistance from your outside system. So let's get a little review of enthalpy first. So enthalpy changes, they can have positive or negative values. So think about this question real quick. What type of processes result in negative delta H's, exo or endothermic processes? Hopefully you shouted exothermic. Absolutely. So exothermic processes are going to result in that negative delta H value. Why? Because energy is being released by the system. So remember, enthalpy is that measure of your stored energy value, right? A lot of people refer to it as the heat content of your system. And so really, if we're talking about changes in enthalpy, we're talking about the changes in the storage of energy in your system. So negative delta H processes result in a net release of energy, which would mean that positive delta H would result in a net absorption of energy, and this happens when we have endothermic reactions or endothermic processes. So, just like some kids I know, the universe wants to get that bread without putting in the work. So it wants to be happy without providing much energy. So in general, endothermic reactions or endothermic processes are less thermodynamically favorable because it has to result in an overall net absorption of energy. So let's take a look at this example right here. What's the sign of enthalpy for the following reaction? So we're going from solid water, ice, to liquid water. So in this case, is energy being absorbed or released? Well, energy is being absorbed. Because overall, we have to break those intermolecular forces between the solid water molecules. So energy must be absorbed to do that. So if energy is absorbed, this is an endothermic process, which would mean that overall this is a positive delta H value. All right, so now we're going to move on to talking about something called entropy. So the first law of thermodynamics, there are three. The first law of thermodynamics tells us that the universe has constant energy. So what does this look like? Well, this would say that any change in energy in the universe will result from a change in energy of the system that you're looking at, plus the change in energy of your surroundings. But think about this. Law of conservation of energy tells us that energy can't be created or destroyed. So really what this is saying is any change in the universe will result in a net zero absorption or release of energy. So the second law of thermodynamics is all about entropy. So entropy you can represent with a capital letter S, and enthalpy you represent with a capital letter H. So entropy is the dispersal of matter or energy in a sample. So essentially what you're measuring in this case is a measure of your disorder, a measure of your randomness of your system. So the universe tends to favor greater disorder. The universe is messy. It's a messy lady. So she tends to favor greater disorder or more mess. So the greater the disorder, the greater the entropy, because your entropy is associated with that measure of disorder. So all objects will have a non-zero entropy value. The only exception is if you had a perfect crystalline solid at absolute zero, which we call 0 Kelvin, then that would have a zero value of entropy, because in that case there's no disorder, right? Everything is perfectly positioned together. There's no motion in your system. All of your atoms are completely still. Okay, so let's talk about some changes in entropy next. So we're going to start off with phase changes. So we're going to do this considering the states of matter of water. So if we think about what solid looks like at a particle level, in water, you have all of your particles of water super close together, connected, held together by hydrogen bonds, which is strong intermolecular forces. There's little motion in your particles, so this is what they look like. As you move to a liquid, you have to absorb energy into the system to get something to melt. So those intermolecular forces are going to start breaking, which means our liquid particles are going to start being a little bit farther away from each other. They can wiggle a little bit more. They're not held together in that rigid structure. And then add even more energy, and you're going to push them to a gas phase. You're going to evaporate. So here your particles are going to be far away from each other. All right, trying to fit those in the box, but still put them far away. So in this system, think about the kinetic energy of your system. If we're in a solid state of matter, we have kinetic energy equals low. As we increase our phase of matter, our kinetic energy of the system increases, but we have to think about the dispersal of that energy, because that's really what entropy is. It's the dispersal of energy in matter. How spread out is it? So although gases tend to have higher kinetic energies because they're moving really fast, they're far away from each other, they can't really form intermolecular forces because they're moving quickly. They can form intermolecular forces, but not often. And if they do, they'll be LDFs, which are really weak, really fleeting, right? So even though gases have high kinetic energy, the dispersal of that energy is also greatest because the particles are spread out, they're moving fast. So the dispersal of the energy is also high. If you compare that to a solid, your dispersal of energy is very low. Your particles are close together. They're not moving very much. The dispersal of liquid is going to fall in the middle. Now, what about the dispersal of matter? Same thing. Your particles, those physical objects, are very close together. So our dispersal of matter is also low. Compared to our gases, they're spread out, they're far apart from each other, they take up more space because they're farther around, so our dispersal of matter here is also high. Water falls in the middle. All right, so if we're thinking about entropy, entropy is a measure of that disorder, a measure of that dispersal, which means for solids, your entropy is going to be lowest. For gases, your entropy is going to be highest. Water is going to fall in the middle. So it's all about that dispersal of energy, that dispersal of matter. So let's think about gases now, just specifically gas particles. So let's say they're at constant temperature and constant pressure. So I have two systems here, two boxes. We're assuming the temperature and the pressure are the same. So what this means is if the temperature is the same, they have the same average kinetic energy. Average KE is about the same. So in these cases, let's think about what it's going to look like with our particles. If we have a high volume, those particles are able to spread out from each other even more. They can move with the same kinetic energy as the ones in the low volume, but they're able to take up more space. So our low volume particles have less space to move around. So high volume, more space. So think about the dispersal then. If you have more space to move around, is something more dispersed or less dispersed? Hopefully you shouted more, Miss Lambert, and you're absolutely right. If something has a higher volume, it takes up more space, or it can take up more space, which means that its dispersal is going to be higher. So for the case of gases, if you have high volume, your entropy is also high. So for this, when we're talking about energy, about same for both sides of this, because our average kinetic energy is about the same since our temperature is constant. So dispersal of your energy is also greatest for your high volume systems. So that would also contribute to the entropy being high. So in this case, entropy is going to be low. Particles don't have as much space to move around, less disorder. Okay, so now let's think about chemical reactions. So in a chemical reaction, generally what you're going to see is if your moles of gaseous products are greater than your moles of gaseous reactants, then your entropy increases. What this means is you're creating more disorder in your system. So let's take a look at this example here. I have 2 moles of solid sodium reacting with 1 mole of gaseous chlorine to produce 2 moles of solid NaCl, table salt. So in this case right here, I'm starting out with 1 mole of gases on my left, but I have 0 moles of gases on my right. So 1 mole reactant versus 0 moles product. So what must be happening here? Well, I'm going from something that's a gas, highly disordered, and bonding it to sodium, creating that ionic salt, that ionic crystal. That's a solid that's held very rigidly. That's a more disordered system. So what we can say here is this is going to result in a negative delta S. The entropy is decreasing. I am becoming more ordered or less disordered. So S is a measure of the disorder. I am becoming less disordered. So becoming less disordered. Oof, running out of room. Okay, so that's a general rule for you. Take a look at the moles of gas on the right versus left, products versus reactants, or reactants versus products in that case. If you have more gaseous products, then your entropy is going to be positive. It's going to increase. Okay, so let's take a look at gases at constant volume and pressure now. So now we're at different temperatures. So in this case, this little graph right here, this is called a Maxwell-Boltzmann curve. So what this is trying to show us is the distribution of your particles as they increase in speed. If they're increasing in speed, what does that actually tell us? Our particles are increasing in temperature. They have a higher average kinetic energy, so they have a higher speed. So if we take a look at a cold gas, what this is showing us is that the average speeds of our gases are going to be lower because our gas is cold. They're not moving around as much. So the number of molecules on this distribution falls at about that point right there. This is saying that this is the average speed of most of those molecules. As you start increasing the temperature, you're going to move that average speed farther on the x-axis, which is saying that the average number of your particles at a higher temperature is, or the average number of your particles at different temperatures is going to spread out. So even though the number of molecules at the peak is decreasing, notice what's happening to the curve. It's flattening. So what this is showing us is there's a greater distribution of those particles over a different range of temperatures. If your gas is very hot, the most of your average particles are going to fall at that speed right there, but the greatest distribution of particles is present. Your particles can have a higher range of temperatures or higher range of speeds. So in this case, gases at higher temps have greater distribution because the the average speed can have more values. Or not average speed, just the speed actually. The speed can have more values. So the distribution of that speed is going to be greater. Your particles distribution is going to be more spread out. So let's think about how that relates to entropy. So if you have high temperatures, your particles are able to spread out more. They're allowed to accompany more different values of that speed, which means they have a greater distribution. A greater distribution of energy, a greater entropy. So high T, high S. More distribution, more disorder, more entropy. So entropy is a temperature-dependent value then. So the dispersion of energy is greatest at high temps. So entropy is greatest at high temps. So let's figure out how we can actually calculate this thing. So just like changes in enthalpy, entropy can be calculated as a sum of entropies of products and reactants. So this formula looks almost identical. But unlike enthalpy, almost all substances have non-zero entropy values. So what we could do with enthalpies is if something had a enthalpy of formation of 0, we could just like take it out of our equation. We didn't even have to factor it in because the value was 0. That's not going to happen for entropies because almost everything, except if it's a perfect crystal at 0 Kelvin, will have a non-zero entropy. So here's your formula. Delta S reaction, remember that little knot right up there. So delta S not reaction means at standard conditions. So at standard conditions, it's equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And here are your units, joules per Kelvin mole. What were the units for enthalpy? Recall. Kilojoules. Okay, so units for enthalpy were kilojoules. We got to remember that because that's important. So this is one of the reasons why I tell you got to put your units in when you're doing these problems. So then if we're thinking about entropy now, entropy units are joules per Kelvin. Why per Kelvin? Because entropy is a temperature-dependent value. Okay, let's get a little practice. Let's do a problem. Okay, so consider the reaction below. This is known as the Haber process. This is one of the most famous reactions that's used in like 875,000 practice problems everywhere. So if you see this, nitrogen gas plus hydrogen gas makes ammonia. This is called the Haber process. Super popular, super familiar. Just get used to it. It's one that's going to show up all the time. So Haber process is for the synthesis of ammonia. Taking two gases, making another gas, and you get some heat released. So first off, before we do anything with like entropy, let's review a little enthalpy. Take a second to look at that reaction. What do you think the enthalpy should be? Drumroll. Exothermic! Yes. So this is an exothermic reaction, which means our delta H is negative. So heat's being released in this process, exo. Therefore, negative delta H. Okay, here we go. Without doing any math, determine the sign of entropy, delta S not reaction. Justify your answer. Okay, we can't do any math. Okay, how else can we figure out entropy? Well, entropy is a measure of disorder. I'm working with all gases here, so let's take a look. How many moles of gas do I have in the reactants? Ooh, all right. Well, I got one gas right here. I got one gas right there. I have 1 mole of nitrogen, and I have 3 moles of hydrogen. So I have 4 moles of gaseous reactants. Cool. All right, now let's take a look at my products. I have another gas in the products, and this time I've got 2 moles of that ammonia. So versus 2 moles gaseous products. All right, so am I becoming more ordered or more disordered? Well, I'm going from 4 moles of reactants to 2 moles of products. This must mean that entropy is going to be negative. I am becoming more ordered. I'm producing less gaseous products in this reaction. So therefore, entropy should be negative. Negative delta S. All right, now let's calculate it out. Let's see if we're right. So using table of values, calculate the entropy of the reaction. So our formula, that's the word, our formula for entropy, oh my goodness, I hope I haven't been mixing those words up too much in this video. Okay, once you keep saying the words more and more, you just kind of start losing it. Oof. All right, so using the table of values, calculate the entropy. So formula for entropy is delta S, not reaction, is equal to the sum of the entropies of our products minus the sum of the entropies of our reactants. So my product here, I have 2 moles of ammonia. So just like enthalpy, this is molar dependent, right? So I have 2 moles of my ammonia. So I have 2 moles times the entropy value for ammonia is 192.5 joules per mole Kelvin. Great. The units for here would be 2 moles, so those units are going to cancel out. I'm actually just going to leave it with writing joules per Kelvin for the rest of this, just to make it easier on myself, because I didn't leave myself very much space. Oof, bad, Miss Lambert. Okay, so subtract out now the entropies of our reactants. All right, so we got nitrogen, 191.5 joules per Kelvin. And I need to add to it now the entropy for the hydrogen gas. So I have 3 moles of that times the entropy, which is 130.6. Oops, come on, 0 joules per Kelvin. All right, so plug this in my calculator. What do I end up with? Delta S reaction is equal to negative 198.3 joules per Kelvin. There's my final answer. All right. So I'm going to leave it at 4 sig figs right there, because the only values that you were given were actually the delta S's for this problem. So I'm going to leave it as negative 198.3. So let's check our sign. Boom, negative. Does that match? Boom, we thought it should be negative. Yay, we're geniuses. Okay, try the next one on your own. Then go ahead and check the answer key. Make sure you got this part down, and then come on back for part 3, Gibbs free energy. All right, so part 3, Gibbs free energy. Gibbs free energy is represented by the sign delta G. This one actually makes sense. G, Gibbs free energy. All right, awesome. Now we're going to talk about this and reaction favorability. So Gibbs free energy, G naught, standard conditions, determines if a reaction is spontaneous or non-spontaneous. Oof, think about what that word means in your everyday life. All that means is it going to happen on its own, or is it not going to happen on its own? All right, so value of delta G tells us if a reaction is thermodynamically favorable or unfavorable. If a reaction's free energy is negative, that means it's thermodynamically favorable. So ultimately, if you have some sort of chemical reaction, there's going to be 2 things that stop it. Either it's going to reach an equilibrium, which we will talk about in an upcoming unit, or it's going to reach completion. It's going to go until everything runs out. So we can calculate the value for Gibbs free energy for these reactions. We're going to start talking about basically if a reaction goes to completion, and then we'll deal with Gibbs free energy for equilibrium reactions later. So just like enthalpy, or just like change in enthalpy and change in entropy, change in free energy can be calculated as the sum of free energies of products and reactants. Look at that formula. What? So familiar. Yes, products minus reactants. But take a look at our units. Bam, kilojoules per mole. So this is really similar to enthalpy, right? But not similar to entropy. So let's deal with this Haber process again. And now we're going to calculate the value for Gibbs free energy for the reaction. So delta G naught reaction is equal to sum of your free energies of your products. I have 2 moles of ammonia. Its Gibbs free energy is negative 16.5 kilojoules. And then I am going to subtract out the Gibbs free energy of my reactants. What? A beautiful number. 0. 0. Yes! So the Gibbs free energy can be 0 for some substances like enthalpy, unlike entropy. So here I can just subtract out 0. Yay, everything is wonderful. So that means that the Gibbs free energy for this reaction is negative 33 kilojoules per mole. Ba-bam, yay! So this reaction has a negative delta G value. So this reaction is thermodynamically favorable. It will happen without external intervention. Okay, so a spontaneous or a favorable reaction is one that favors formation of products. So that means that the reaction, it occurs on its own without external intervention because the formation of the products puts things in a lower energy state. So this will occur without continuous input of energy, external intervention. Non-spontaneous reactions require the continuous input of energy to proceed. So it doesn't mean they can't happen. It just means you got to continue putting energy in, and then you'll make it work. I do want to point out that if a reaction is spontaneous in one direction, the reverse direction will be non-spontaneous. So any reaction can get flipped. So if I take the Haber process in this direction favors formation of ammonia. It's thermodynamically favorable when we're making ammonia gas, which means if I flip that reaction and now I started with ammonia and I wanted to break that down into its components, into nitrogen and hydrogen gas, this would not be thermodynamically favorable. The value for this would be positive 33 kilojoules per mole. Therefore, non-spontaneous, non-favorable. Okay, so let's talk about reaction spontaneity for a second. So if we have a negative delta G, a negative Gibbs free energy, this is going to be a spontaneous reaction. The other vocabulary term that it could be called is called exergonic. This is an exergonic reaction. So I know you're probably thinking, exergonic, exothermic. Oh my God, Miss Lambert, what? I know, but there is a difference between the two. Exothermic is talking about releasing energy in the form of heat. Exergonic is talking about releasing energy, putting things at a lower energy state in terms of its Gibbs free energy. And this is just energy being released. Doesn't have to be specific to heat energy like exothermic and endothermic processes do. So if you have a positive delta G value, this is a non-spontaneous reaction, not thermodynamically favorable. Take a guess what this one's going to be called. Endergonic reaction, not endogonic. Oh God, I know our lives are so hard. It's gonna be fine. Endergonic, that's how you remember this. That's what this one's called. All right, so what does this actually mean? Let's take a look at the graph. So over time, how is the Gibbs free energy of this system changing? Well, the reactants start out at some energy and your products end at some energy. In this case, your products are ending at a lower energy. Energy is being released from your system. So why don't all reactions that are endergonic just magically happen all the time around us? Well, you also have to remember there's this little term right here. So we talked about this in our last class, but we haven't talked about it since. In order for a reaction to occur, there is still some minimum amount of energy that your particles have to collide with to make that reaction happen. And this is what's called your activation energy, E sub A. So particles still do have to collide with each other with a certain amount of energy before it can just boom, magically happen. So for endergonic reactions, energy has to be added to your system, boom, 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 and then your products end higher in energy than your reactants. So we have already learned the universe will favor exothermic reactions, therefore it will favor negative enthalpies, negative delta H. It favors more disorder in your system, which means it favors positive entropy values. But we also have to remember entropy is a temperature dependent quantity, which means overall thermodynamic favorability also depends on temperature. So Gibbs free energy has one more equation that you can use to put it all together. If you know the change in enthalpy, and you know the change in entropy, and you know the temperature at which your system is your temperature at which your system's at, you can calculate the Gibbs free energy for your system. So let's think about when a system would be thermodynamically favorable, including all this information. So let's say that you have a negative delta H value, or your delta H is less than 0. And let's say you have the opposite situation for your entropy. Let's say your entropy is positive. So in this case, we have our negative H, our positive S. For this, the universe always favors negative enthalpies and it favors positive entropies, which means when you have these two situations together, Gibbs free energy will always be less than 0, which means it's favorable at all temperatures. So no matter what the temperature, if your H is negative and your S is positive, you're going to have a Gibbs free energy value that comes out to be negative, which means it's going to be thermodynamically favorable, no matter the temperature. Okay, so now let's think about what happens if the opposite is true. So let's say you have a positive H and you have a negative S. Okay, so in this case, if you have something positive over here, positive H, and you have a negative S, something positive is subtract out a negative. Your two negatives here cancel to become a positive in the equation, which means that no matter what, delta G is always going to be positive. And if delta G is positive, no matter what, it's not thermodynamically favored. So no matter the temperature value here, this will be favored at no temperatures. Gibbs free energy will always be positive. It will never be negative. Therefore, it will never be favored. And that also makes sense, right? Like if enthalpy, negative enthalpy values are favored in a system because it's exothermic, if entropy values are favored when they're positive, but you have opposite signs there, that makes sense that it's not going to be thermodynamically favorable because neither of the individual components are thermodynamically favorable. All right, so now let's take a look at how we can mix it up. All right, so let's say in this instance, you're going to have a positive enthalpy value. Oof. So this on its own is not really favored. Delta S, let's say you have a positive value as well. This is favored for entropy. So if we put them together, let's think about if it's going to be favored overall with the Gibbs free energy. So, okay, back to our equation. We have something positive, our enthalpy. We're subtracting out some T times a positive value here. So when is Gibbs free energy going to be negative? When's it going to be less than 0? If this number is bigger than this number, then let me flip it. Nope. If this number is bigger than this number, then that means that overall this term wins out in the equation, right? So let's say I have like 1 versus 32. 1 minus 32 is going to get me something negative. So if my entropy and enthalpy values are both positive, this term wins out when T is large. If T is significantly big, it's going to change it so that term T delta S is a very large number, which means that it's going to subtract out a very large number, which means overall your delta G is going to be less than 0, and it will be thermodynamically favorable. So this situation is favored at high temperatures. So I think you can probably guess without doing the math what's going to happen for this last one, but let's work it out just in case. So let's say in this situation you have both negatives. So now your enthalpy is a favored term, entropy is not, okay? So in this case, you have something negative, subtract out T something negative. In this case, if this number is significantly larger than this number, this term overall is small, then that means that you are going to get something that could come out to be negative, because the negative plus something small positive will still overall be negative. So that means that this situation is going to be favored when they're both negative at low temperatures, because that T delta S term overall will not be positive enough to push it over the 0 line. So let's take a look at an example. We want to determine delta H, delta S, and delta G knots for the reaction at 298 K, standard conditions. Then determine if the reaction is favored or not. So to determine if the reaction is favored, we have to calculate delta G, and we have to calculate delta H and delta S in order for us to get there. So to calculate delta H knot of the reaction, we do enthalpies of our products minus enthalpies of our reactants. To calculate delta S knot, we do enthalpies of product, or entropies of products minus entropies of reactants. Then to calculate delta G knot, we put it together. Delta H, subtract out T, delta S. Here, our temperature is 298 Kelvin, so we can add that into our equation, 298 K times delta S. And then whatever you get here, you compare the value. If it's positive, not favorable. If it's negative, it is favorable. So the only thing, I'm going to let you work this one out on your own doing the actual values, but the only thing I want to remind you of is your units. So the units for delta H, you're going to come out with our kilojoules. Units for delta S, you're going to come out with our joules per Kelvin. The units you want delta G in are kilojoules, which means that at the end of this process, when you get joules per Kelvin here, you want to convert it to kilojoules per Kelvin. And then when you plug it in here, what's going to happen? Kelvin cancels with Kelvin, and you're left with kilojoules minus kilojoules, and then your units work out. So go ahead and try working out the actual value for this problem. Check in with the answer key. And then the only last thing that I have to tell you here is you can still determine the Gibbs free energy for something if it's not at standard state. The only thing is you have to take into account the temperature, right? Which is fine, because you're just plugging in a different value for that T. So I do also want to warn you of one last thing. Delta H and delta S honestly do not significantly change with temperature, but delta G does. High T and low T are big factors that play into thermodynamic favorability. So if you are changing the temperature of your system, you really are going to have a large effect on your free energy of that system. So you can't just immediately look at a number and think, oh, that's kind of like relatively low. I can call it what it is. I think it's going to be this. No, you should really actually work out the math. It's going to be the easiest thing to do for you. So I'm going to let you work out the value to this problem, and then I have some extra practice problems for you on these next couple pages. Go ahead and work out those as well. Check in with the answer key, and then if you have questions, let me know.